Hi everyone, I'm Kwan, a PhD student in MIT CSAIL. Today I'll be presenting some work that was completed with Tej Tria and Neha Narula while I was interning at the MIT Digital Currency Initiative this past summer. More specifically, I'll be presenting our work on verifiably delaying adaptive adversaries in consensus. I'll be explaining what each of these terms mean in the following few slides. Just very quick to start, I will define consensus. The consensus involves schemes or protocols meant to ensure participants reach agreement in a decentralized network. Some desirable properties of consensus include, of course, having everyone agree on the same value. Suppose you have the following set of participants which propose the values A, B, C. These values can be anything, for example, blocks you may want to add to the blockchain or functions you want to execute in a distributed database or code base. If everyone talks to everyone and is honest about their proposals, they can simply decide on a value like the lexicographically first value, which in this case is A. Furthermore, we want the additional property that if everyone starts with the same value, they also agree on the same value. For example, if everyone starts with B, they should agree on B, not A or C. In a real-life distributed system, not everyone participating in consensus is honest. Thus, we also want the property that all honest players can reach agreement, even in the presence of adversaries. Here, even if there is an adversary, all the honest participants should reach agreement on the value B. Two properties by which we measure the effectiveness of a consensus protocol are liveness and safety. Liveness is defined as a property that progress is always made in the system. This means that, for example, blocks are continuously being added to the blockchain. Safety is defined as a property that all honest players agree on the history of values committed to the chain. For example, all participants of a crypto system should agree on the history of transactions that were performed. Throughout this presentation, we assume the synchronous model in which agreement over values proceed in rounds, and there is a fixed maximum amount of time messages can be delayed. In light of the applications of consensus to large crypto systems, we want a consensus protocol that obeys liveness and safety in the presence of millions of participants. This is far too many participants for everyone to be able to send messages to everyone before these messages flood the network. Thus, an additional desirable property for consensus protocols for these systems is that we want only a small number of honest nodes to speak before consensus can be reached. Furthermore, adversaries are more motivated in these systems to perform targeted attacks. Since only a small number of participants are speaking, adversaries can, for example, launch attacks only on the speaking participants. A valid strategy, then, is to observe the network for messages sent and then attack the important players in the consensus protocol. Thus, we also want protocols that are robust against these strong adversaries. Finally, some existing crypto systems already achieve the two desirables above. However, each has some caveats, which I will mention later. Specifically, in the context of protocols based on proofs of work, we want to create a protocol that has the two desirable properties above, but avoids energy-wasting proofs of work that can be parallelized using special hardware. We'll first start with the first property. One way by which current crypto systems deal with only having a small number of participants speaking is via cryptographic sortation as used by the Algorand crypto system. Cryptographic sortation is a procedure by which all participants in the protocol elects a small committee at random. Then the consensus protocol is run among the small number of participants, which makes a decision and then informs all other participants of their decision. Some characteristics of cryptographic sortation as used by Algorand include having a small number of proposers which propose blocks, and also having a small number of voters which vote on the blocks proposed by the proposers. In this case, if the number of proposers and voters are polylogarithmic in n, where n is the total number of participants, the total number of messages sent by these proposers and voters to everyone would be O of n polylog n, which is a much smaller value than n squared when you consider n to be on the order of millions or billions of users. Another important characteristic of cryptographic sortation is that each individual decides committee membership secretly. This can be done via cryptographic primitives called verifiable random functions, or VRFs. Although membership is decided secretly, committee members can inform others and prove their membership later on. Such ideas are used in a variety of crypto systems, including Algorand, Dfinity, Filecoin, Witnet, and others. Thus, this concept of cryptographic sortation allows us to satisfy our first desirable property. Now we'll talk about the second property. Note that from this point forward, I'll only talk about the remaining properties for protocols that satisfy the first property. First, very quickly, traditional consensus protocols mainly considered static adversaries. So what are static adversaries? Let me quickly define that. Suppose we have a set of Byzantine nodes. These Byzantine nodes are decided before we run our consensus protocol, hence the name static. Then we run our consensus protocol and reach consensus. But large monetary gain has led to stronger adaptive adversaries. They first observe the network before attacking the crucial players. Initially, there are very few or no Byzantine nodes. Then the protocol is run. Suppose the protocol elects a leader. Then the leader sends a message. By the time the leader sends a message, the adversary would have known that the highlighted player is the leader. So after the leader sends the first message, the adversary pulls together all his resources to mount an attack against the server of this leader. For example, the attackers could choose to DDoS the leader, or bribe or hack. Any number of such attacks may work. Then the corrupted leader can perform malicious actions immediately, potentially violating both the liveness and safety of the protocol. Now we'll take a look at some case studies and observe how adaptive adversaries can break the protocol in each of these cases. In the first case, adaptive adversaries can violate the liveness of protocols which have predictable leader schedules. You can corrupt the leader before they are elected and have them never send out a proposal. Even if the leader schedule is not predictable, the adversary can corrupt the leader right after they send their first message. For example, they can corrupt every elected leader and then send many different proposals, making voters unable to decide on the same proposal. This would also violate liveness. Finally, if there is a small committee, the adversary can corrupt the committee right after an election and send votes for every proposal or some subset of the proposals to different participants, thus potentially causing the participants to believe that different proposals are committed. This would violate safety. So cryptographic sortation solves the first problem with the predictable leader schedules. But by itself, it does not solve the problem of corrupting leaders and committee members after election. Player replaceability solves the problem of corrupting a leader or committee member after election by having each person speak only once before the next committee is elected. To ensure player replaceability, many current systems use the key erasure model, which makes participants erase their current keys and generate forward secure new keys before announcing their leader or committee membership. Thus, even if an adversary corrupts them, they cannot send a new message using the old keys because these keys have been erased. To give a bit of background on the model, in the key erasure model, it is assumed that keys can be erased at will, arbitrarily, from a replica storage without any recovery possibilities. Such an assumption is difficult to realize in real life since complete erasure on hardware and in software is difficult to accomplish. For example, hardware failure could prevent a key from being fully erased. Similarly, fault-tolerant software backups and human errors in software could also prevent full erasure. Furthermore, there could exist even an incentive scheme to retain and sell old keys. Thus, it seems important to explore alternatives to key erasure to solve the problem of corrupting leaders and committee members after election. Recently, a number of researchers used vote-specific eligibility instead of the erasure model to determine votes for a specific subclass of consensus called binary Byzantine agreement, or BBA. In BBA, participants either agree on the digit 1 or 0. So the set of possible proposals a leader can make consists only of 1 or 0. In their protocol, one can mine a vote by passing into the VRF or cryptographic sortation function either 1 or 0 and the round number. Honest replicas mine a vote for one of 1 or 0. Adversaries can mine for both, but it is difficult to obtain enough votes for 1 or 0, probabilistically speaking. Committee membership is then tied to a successful mining of a vote. The natural extension of this protocol then is to pass in block proposals to the vote function. So pass in arbitrary block proposals to the vote function in order to mine a vote. However, the adversarial strategy is then to try an arbitrarily large number of transactions and blocks to attempt to create a block that obtains a disproportionate number of adversarial votes. This situation then dissolves into proofs of work in which the adversary will parallelize the grinding of various blocks, and thus the greater the computational power of the adversary, the greater the ability to get more votes or to grind more votes. Consensus through herding presents a solution to this issue by assigning scores to transactions by age. This essentially ensures that older transactions are included in a committed block and limits the ability of adversaries to grind through many new blocks. However, it appears that the safety and liveness of such a scheme is tied to this temporal ordering of the blocks. And it is unclear how such a scheme can work with other priority functions on the blocks, such as determining priority based on transaction fees, which are used in real-life crypto systems. Thus, although previous work provides guarantees for these two items, they are not quite the optimum ways to provide for these desirables. So let me just give a quick recap. We want a protocol that protects against adaptive adversaries without using the key erasure model, and also preventing against vote grinding or block grinding. Now I'll talk about our solution. So the intuition of our solution is the following. Each block proposal takes some number of time steps which must be performed before the proposal can be sent out. This number of time steps can be performed even by parallel adversaries, and they must be performed even if the adversaries have parallel abilities. Rounds take some fixed amount of time guaranteed by our assumption that message delay is fixed in a synchronous network. Thus, we make it impossible to perform the time steps necessary for two different blocks before the round rolls over to the next round. So let me just quickly restate that again. We are able to ensure this property because since rounds are fixed, it is impossible to propose two different blocks by performing the necessary number of time steps before the round rolls over. You just don't have enough time, even if you have access to parallel processors, to perform the necessary time steps before the round rolls over to the next round. Thus, this is intuitively a way to commit to your block before you send it. And an adaptive adversary does not have time to commit to a different block in the same round. In our protocol, we use a cryptographic primitive called a verifiable delay function, or VDF. Such a function requires, say, d-sequential time to compute, even on a parallel computer, but the output can be quickly verified by anyone. Instead of giving the full cryptographic definition of VDFs, I'll just highlight some key properties. First, honest parties take the same amount of time to compute the VDF, not much more than d-sequential time. Second, adversaries must spend at least d time, even if they can parallelize the computation among polynomial processors, arbitrary polynomial processors. Third, an adversarial algorithm cannot compute an output that is not equal to the intended output. This means that outputs are unique given a unique input. Finally, this is very important, verification of the computation is fast. So if you have a solution to the VDF and you send the solution and its proof to everyone else, they can verify that you computed the VDF correctly in a very short amount of time. So here is a simplified visual diagram of our protocol. Our paper contains a full detailed description of our protocol, as well as the proofs for its properties. We use 5 different phases in our protocol. In the first phase, the leader, which is determined randomly via a call to a VRF, computes the VDF associated with the block it wants to propose. Suppose let that block be M. Then it sends both M, the block it wants to propose, and the computed output from the VDF to everybody who's participating in the consensus protocol. Then each participant of the next voting committee computes the VDF associated with their vote. There are log squared n members of the voting committee that is also determined randomly via queries to VRFs. So after computing the VDF associated with their vote, they then send both their vote and the VDF output to everyone. So you proceed like this by electing 3 more committees, proceeding for 3 more rounds until everyone has received at least 2 log squared n over 3 votes on a particular block. And these log squared n over 3, 2 log squared n over 3 votes must hold for the same block for all 3 of the voting rounds. So that's it. So in conclusion, by using VDFs and the number of other observations necessary to the implementation of our protocol, we propose a new consensus protocol that satisfies all 3 properties and hopefully will lead to efficient, safe, and secure protocols in practice. And I'm happy to take questions now.